Hello, today we're going to be talking about hash tables. Today's topic is very important, not only because it's one of the most basic data structures, but also it is really commonly asked in coding interviews. So coding interviews can also ask you to implement a hash set or a hash map without using any built-in libraries. So if you're preparing for those kind of interviews, you really need to know how hash tables work. So in this video, we're going to talk about things like what hash tables are and also what is a hash function. We also need to talk about collision handling, etc. And after knowing how hash tables work, you'll understand why hash tables can be so fast when it's trying to insert, delete, or search data. Okay, so like always, I'm going to first explain the basics with diagrams and animations, and then we can go and code what we learned in Go. Okay, so let's dive in. So there is this array and we've got a bunch of names stored in it. Let's say you want to search for Randy. You'll have to go through the whole array one by one until you find your match. And this array is pretty simple, but in reality, arrays are going to be way much larger than this. And using brute force to find Randy is going to be pretty inefficient. But let's say there's a way to find out which index Randy is in. And surprisingly, we can find that out just with the name Randy itself. We'll be able to find where Randy is right away because we know that it's stored in index 82. This is the main idea of a hash table. So the thing that can turn Randy into 82 is something we call a hash function. We input Randy into the hash function and it's going to spit out 82. And we call this output number the hash code. And that will be the location of Randy. This is possible because when we're storing data, we put Randy in a hash function, which will give us 82. So we store it in the location 82. And later on, when we're trying to search Randy, we put Randy in the hash function, get the hash code, which would be 82, and then go to that index 82 to find Randy. A data structure that has data stored in this way is called a hash table. You can see that hash functions play a pretty important role in these kind of data structures. Let's look into hash functions a bit more. I'm going to give an example of a hashing algorithm. I'm just going to give an easy example. Each letter of the word Randy will be converted into its ASCII code. This just means that we're going to turn each letter into a number. And then we sum it up and divide it with 100 and get the remainder. So why is it 100? Because that is the size of the array that we want to store the name into. In this case, the resulting hash code will always be something between 0 and 99. So we store Randy at index 82. And we're going to put Eric into the hash function and get 91 and store it. And we're also going to insert Butters, Stan, and Kyle in the same way. And when you're trying to find a word, let's say we want to find Stan. We would put Stan into the hash function, get the hash code, and easily search it in the hash table. This sounds perfect, right? This seems like the best data structure ever. But there is something we need to talk about when we're dealing with hash tables, and that would be something called collisions. In the hash function example I just gave, there might be a chance that two names can have the same hash code. Let's say we want to store two names, Randy and Eric, and we want to store it in an array of a size 7. If we put them in the hash function, they will be giving out the same hash code. So if we had stored Randy in the array, and then after that we try to store Eric, that index number is already taken by Randy, so we can't store Eric. Handling these kinds of situations is called collision handling. So collision handling will let us find a way to store both Randy and Eric in the array. We'll look into two ways of collision handling, open addressing and separate chaining. First, let's see what open addressing is. If the spot for Randy is already taken, we just store Eric in the next index. And when we later on try to search Eric, we first go to its original position where the hash functions tells us to go. And if it's not there, then we'll look into the next index. Although we need to add an extra step when we're searching, this would still be faster than just searching all the indices one by one from the beginning. But with open addressing, as the array gets filled more and more, the names would get further and further away from where it should be. and we will start to lose the benefits of hash tables. So this would lead me to explaining the second collision handling method, which is called separate chaining. A simple and easy way to explain separate chaining would be storing multiple names in one index. How? By using linked lists. So instead of storing the names in the indices of the array, each index will hold a pointer that points to the head of a linked list that has a list of names. If you don't know what linked lists are, there's a video explaining that, so I'll put a link in this video. Linked lists will be able to grow and shrink dynamically, so we don't have much limitations toward the size of the data we want to store, and using the combination of an array and a linked list makes separate chaining a very fast and effective method for hash tables. So we talked about two ways of handling collisions: open addressing and separate chaining. In this tutorial, we will be coding separate chaining, so we need to look into the details of how we're going to insert, delete, and search the keys. So from now on, we will call the names to be stored as keys, and the linked lists in the array index will be called buckets. We call the names keys because hash tables are used for storing key and value pairs. For example, the name Randy can be associated to a value that holds data or other information. Let's look at how we can insert a key into the hash table. We'll first get the hash code by putting the key in a hash function, then go to that certain index in the hash table array and insert it right there. But because we are doing separate chaining, we will have to store it in the bucket. Each key in a hash table will have to be unique. So first we need to search the bucket and check whether that key already exists in the bucket or not. And if the key doesn't exist, we will then add the node represented by the key into the linked list. Let's add Eric that has the same hash code as Randy. Like we do in a linked list, we will make a new node and we will let that new node become the head node and make that node point to the node that used to be the head node before. When we're searching for a key, we'll first find the bucket that holds the key by putting the key in the hash function, and then go to that bucket and search the bucket one by one until we find the key. And if we want to delete a key, we go to that slot, just like searching and inserting. We go to that slot and look for the key in the bucket, and then we disconnect it from the bucket. We do that by letting the previous node skip the node that we want to delete, and make it point to the next node. By using linked lists and arrays, we're getting the benefits of an array where we can immediately access a slot, and that lets us insert, search, and delete a key faster compared to other data structures. Let's talk about how fast it can be by looking into the time complexity of hash tables. The time complexity of hash tables for inserting, deleting, and searching is expected to be constant in an average case. Comparing that to some other data structures we talked about in the previous videos, that is pretty good. You can think of hash tables with separate chaining as a combination of the benefits of arrays and linked lists. The fact that arrays let us instantly access the data, that lets us search, insert, and delete data very fast. But like always, there's a worst case scenario. If all the keys collide with each other, so all the keys that you want to store have the same hash code, the hash table would become more like a linked list, and it would take more time to insert, search, and delete. So in that case, the time complexity would become O of n. But that is the worst case scenario. In general, a hash table is expected to have a constant time complexity. In this tutorial, we're going to implement a simple hash table with separate chaining in Golang. There is a type called maps in Go, and that actually implements the hash table itself, but we also need to understand how to implement a hash table without using any built-in libraries or any built-in functions. So that's what we're going to do here. So let's go and do some coding. So the hash table part is going to have the insert, search, and delete, and the linked list bucket part, the buckets are going to be linked lists, will also have insert, search, and delete. So first of all, let's go and write down the things that we need to do. So first we need to have like a hash table structure, and we also need a bucket structure, insert for hash tables, and we need a search for hash tables, a delete. So these three are going to be methods for the hash table. And for the bucket, we also need to implement insert and search and delete. Okay. So we have to build a structure for hash table and bucket. These are going to be for the hash table, and these are going to be for the bucket. And other than this, other than the structure, the methods for hash table and the method for buckets, we also need to define a hash function. And we're also going to do init. This is also going to be a function that initializes the hash table. Okay, so for the hash table structure, the bucket structure needs to be a linked list. So that's why we need to have a linked list, and also we need bucket node structure. Okay, the hash table is going to hold an array. So hash table will, and we'll just call it array. The array size is going to be a constant. So we have to define a constant for the array size because we don't want to hard code the number 7 inside the hash table struct. And that type is going to be a bucket. We didn't define this yet, but we will define it right after this. So the array size is going to be the size of the array. And because we need to use this here and there, not only the hash table, but when we're doing like writing the hash function, we also need to use that. So I'm going to make it as a const. And right now I'm just going to put 7 in it. So we didn't define this yet, so we're going to do this here. A bucket is going to be a linked list. And like we did in linked lists, we're just going to put the address of the head node in the bucket. And bucket node, we didn't define that yet. We're going to do that here. Okay. And like we did in linked list node, each bucket node is just going to hold the key, and also it needs to have an address pointing to the next node. So we'll just call it key, and that is going to be a string, like the names, like Eric, Randy. And then the next will be an address of another node, another bucket node. Let's go and just try to like create some of the structures and just see what they have. And I'll just create a hack. Okay, and if I open the terminal and try to run it, so we have an array. This, we just like printed out the whole thing. A hash table, the test hash table right now has an array size of 7, and the array is empty right now. Okay. Each slot of the array, it has to hold a bucket. So we're going to make a function that initializes this particular hash table and create a bucket into each slot. So it's not going to take in any parameters, any arguments, but it is going to return a hash table, an address of a hash table. So, and let's go and create a new hash table. We're going to create a new bucket. So we have to be creating 7 times. So we're going to put it inside a for loop to do that. So for I. Okay, so right now what I did was I created a for loop that can loop through each of the slots inside the hash table array, and inside there I created a bucket and I put it in. So here I'm going to put test hash table as an init function. In that case, this is going to return a hash table where each slot has a new bucket inside it, and it's going to return that. So let's see what this shows. Run it. And unlike last time everything was inside the array was nil, but this time in each slot of the array we're going to get an address, because in each slot we created a bucket and we put it in. The next step, we're going to actually do the inserting and searching and deleting. So we're going to have a pointer receiver of a hash table. It's going to be a method of the hash table, and it's going to take in a key like Randy or Eric. So we'll call it key, and it's going to be a string, and it's not going to return anything. And we'll write what's going inside here later on. We're just going to copy this and paste it here. It's a search because this is the search method. We're going to return true if that key is inside the hash table, or false if not. Is for delete. So this is for the inserting, searching, and deleting of the hash table. When we're doing these three things, the first thing we need to do is to put this key inside a hash function and get the hash code, call it index, and we'll go hash, and we'll put the key inside it. We did not actually create this function yet. That is going to be our next step, but we're just going to write it out first. Okay, because I want the process of writing this code to be organized. Okay. So now that we need this hash function, we're going to go and implement it here. So hash, and it needs to take in a key, a string. So we'll just go key string, and it's going to return an integer. So int. Okay. We're going to just get the ASCII code for each character, sum it up, and divide it by the array size and get the remainder. That's what I'm going to do. I'll first go sum to get the sum of each ASCII, and I'll just say 0 to just initialize it. And then we need to use a for loop to loop through each character of the key. So that's going to be for, I'm going to throw that out, and the range of key, and I'm going to put it into sum int b. Right now what this is doing is, let's say if I put in Eric, then it's going to loop through each of the characters in Eric in the string. So E, and then I'm going to turn that E into an integer, and I'm going to add it to sum. I'm going to add it to sum. The next for loop, I'm going to go to R in Eric, and I'm going to add it to sum, and that's how I get the sum of each of the characters. And I'm going to return sum and get the remainder of the array size. Let me just do a little test here. I'm just going to comment this out. Oops. Yeah. And comment, I'm just going to comment everything out. Okay. So we get 4 for Randy, which is correct. Okay, so I just wanted to check if the hash function was working all right. And for the insert, after we get the hash key, turn it into a hash code and put it in the index, we're going to go to that array slot. So in that hash table, there's going to be an array, right? And I'm going to the slot of index of that array, and I'm going to insert. I'm going to insert the key in this slot. Each hash table is going to have an array. Right now it's having 7 slots. Each slot is going to have 1 bucket, and inside that bucket I'm going to insert this key. So that's what we're doing right now. I did not define this method yet. That is going to be my next step. So I'm going to go and make this method over here. This right now is a bucket, so it has to be a method of a bucket. So I'm going to go and define insert right here. It has to be zero is the bucket. So the first step would be to get a key and create a bucket node with that key. I don't like that. I'm gonna go like this. I'm gonna set the parameter as k. I'm going to set this new node as a head, and then I'm going to make the next of this new node point to the head that was there before. So right now the new node next will become the current head. The head is going to become the new node. So let's go and check this over here. And I'm going to just create a bucket with nothing inside it. And then a test bucket, insert, Randy. And I'm going to start to use breakpoints instead of printing everything in the console. So I'm going to launch the debugging. I'm going to step over, and that means I'm going to see the results of this. So I executed this line and we're going to go to the next. So test bucket should now have Randy inside it. So let's go and check that. So inside test bucket, this is the address of the bucket. And if you go inside here, it means we're going to go to that address, which is going to be like the actual bucket. And inside there, the head is going to have this address, which is a bucket node. And this is an address. So this means we're going to go to that address, which is going to be a bucket node. And we're going to see the contents of that, which is the key Randy. So we found out by debugging that we actually have the key Randy stored inside this test bucket. Okay, I'm going to stop by pressing that. And so let's first write up the search method. We're going to jump to each of the nodes inside the bucket, inside the linked list, and see if it's a match with the parameter k. So first we need to put the head in the current node. We're going to keep on looping until we find a match. So what we're going to do is we're going to jump to each of the nodes inside the bucket, inside the linked list, and see if it's a match with the parameter k. So first we need to put the head in the current node. Current node is going to indicate that we're doing the, we're going to compare that node. And it's going to be like a while loop. We're going to keep on looping until we find a match. So we need to loop until the current node is empty. So that's going to be expressed like this. And we're going to find whether the current node is a match to k. So that's going to be like node.key. If there is a match while we're doing we're going to find a match for the current node. If the current node key is a match with k, which is what we're trying to search, in that case we're going to return a true right away. And if not, if it's not a match, we're going to update the node to the next node. So if we keep on doing that and we went to the end of the node and it turns out to be empty, we're going to come out of that loop. So we're going to come out of here, and that's going to mean because we looped everything and it was not there. So we're going to return a false. So that's the end of search. Let's try to search here. Test search, and we will also search for everything there. And I'm going to just go down and use it like so you can see that we inserted Randy. So when it searches for Randy, then it's going to be true, and when it searches for Eric, it's going to be false. So now that we have the function search, we are going to put an if statement here saying that if search k is not there. So this means if k doesn't exist in B, in that case, I want to execute this. And else, I am going to fd say already exists. I'm just going to comment these ones out, and I'll try to insert Randy again. And let's see if we can get that statement saying Randy already exists. The last step, we're going to implement the delete method of the bucket. So delete will take key and delete. The linked list will be deleting the current node by skipping the current node and making the previous node point to the next node. And we can't do that if we actually go over the previous node. So that's why we're going to put each node into a previous node and express the current node as previous node dot next. Okay, so we're going to go this and into a previous node. And everything is going to be very similar to the search method, but instead of saying current node, we're going to put previous node dot next. You know how in the search we said for current node is not nil, we're going to go for previous node dot next. This is the current node. And while this is not nil, we are going to loop it through and update it. So we're going to put the updating part first. Previous node will be the next previous node, which is the current node, dot next. And this is where we're going to put the if statement. If this part over here, if current node dot key, which is previous node dot next dot key, is equal to k, in that case we're going to delete. And how we're going to do delete, we're going to set the previous node next to previous node next dot next. But when we're doing the delete, we need to be careful about just one more thing. Because we're putting the head in the previous node, we're missing one case where the actual matching key is the head. So we have to put in an if statement here. If the key of the head is actually the match to what we're trying to delete, so it's going to be b.head. So we're resetting the head of this bucket to the second node, which is b.head.next. And after we've done that, we want to come out of the method, so we're just going to go return. So this is going to just end everything and finish the method. I'm just going to do a very simple test saying instead of this, I'll just go delete Randy and search Randy and see if it returns a false. So and so it's returning a false because we successfully deleted Randy. So now that we implemented delete, we implemented search and insert for the buckets. Now let's go and finish these up, which is kind of like the last step. So I'm just going to uncomment everything. And here this is going to be array-index.search key. And this is going to return a Boolean, so we'll have to return that. Return. And in delete, this is also, right now we're going to the index, and then we're going to go to that bucket, which is h.array_index, and we're going to delete the key. Okay, so this is actually the end of the coding. Now we're just going to go and see if we can just debug it and see if and just check if everything is working fine or not. And I'm going to call this hash table. I'm going to initiate a hash table with a size of 7. And first is Eric. Eric, can you put a breakpoint here? So I'm going to launch it. And let's see what we have. So we are at the first insert. We didn't execute it yet before we actually press the step over. So the step over is going to let us execute this and go to the next step. Right now in the hash table, we inserted Eric. So Eric is, the hash code for Eric is 4. So we can see it over here. Eric is over here. We're going to step over to the next. Kenny is added, and the next node is going to be Eric. So this is one bucket node. The bucket node is going to hold the address of the next, where we can follow through here. So Eric would be the second node. The next over and and the next is going to be stan, which hash code is 2, so that's going to be in here, stan. And we're going to step over and over, and it's going to be Randy, which is hash code 4 again. So it's updated over here. So the head is going to be Randy, and you can see all the other nodes are kind of like pushed to the next. So now that we added all of them, let's start deleting some. Hash table dot delete. Let's delete and we'll launch it. So right now we're here in stan. Stan was in hash code number 2, and when we step over, we're going to see this disappear. So step over, and you can see hash code number 2, the location number 2 is now nil. So we successfully deleted it. We can also try to search it. And because we deleted stan, it's showing false, and we didn't delete Kenny, so it's showing true. If this video was helpful and you want to see more of my videos, please subscribe to this channel, and thank you so much for watching until the end. I don't think many people do. Okay, thank you so much, and I'll see you in the next video.